In this video tutorial, we will continue our lesson introducing the quantum mechanical model of the atom. Specifically, we will discuss how electrons can be represented in diagrams and electron configurations. Now, the next thing we want to talk about is how can we represent electrons. The first way is to use orbital diagrams, which we've already seen over here, where we fill in the individual electrons in this box, if you will, to represent each orbital in a given energy level. So for instance, s orbitals, there's only one suborbital type. P orbitals, there are 3 suborbital types, and d orbitals have 5 suborbital types. And as you can see, the first energy level only has one type of orbital, s. The second energy level has 2 types of orbitals, s and p. Third energy level has 3 types, and fourth energy level should have 4 types. It's just not shown in this particular diagram. Now, there are guidelines for filling in these orbitals. You can't just put electrons anywhere you want. So let's go over the rules we use to show us where to place these electrons. The first is called the Aufbau Principle. So Aufbau is German for building up or construction, meaning each electron is added to the lowest energy level available until all electrons are accounted for. So remember, when an electron is most stable, we say it's in its ground state, so at the lowest possible energy level it can be. So always fill the energy diagrams from the lowest possible energy level to the top. You can't just put electrons anywhere at the top you want. They must start from the bottom and build their way up. Now this chart over here helps us by telling us which shells need to be filled out first. I usually see students draw this out on the top page of their test as soon as they get it. They typically find it easier to answer questions when they see it in front of them. So drawing this out is pretty straightforward. It follows a pretty regular pattern. 1, 2, 3, 4, 5, 6, 7, 8 in the first column to represent the energy level, or your principal quantum number, followed by S, P, D, and F. So there's going to be 4 more columns representing the 4 suborbital types. Then you just go 1, 2, 3, 4, 5, 6, 7, 8 for the S, 2, 3, 4, 5, 6, 7 for the P, 3, 4, 5, 6 for D's, 4 and 5 for F's. So each time you're just forgetting the ends of this. So it's almost like a Pascal triangle. Not really, but it's a repeating pattern anyway. This also helps you to remember that s orbitals have a 0 value for L, P, L value is 1, D, L value is 2, and F, L values are 3. We then follow the arrows to show us the energy levels from lowest to the highest. So of course the lowest energy level is the 1s orbital. After the 1s, start the next arrow, and we go 2s. So notice how it goes from 1s, the next energy level is 2s. After 2s, start the next arrow, 2p. So then we go 2p. Then after 2p, we go to 3s, 3s. Then after 3s, we have a 3p, 3p. But then here's where it gets weird. Most people would think you would start 3d, but no, the 4s orbital is actually lower energy than a 3d orbital. So we have to fill in the 4s orbital first, followed by 3d. That's why 4s, as you can see, is slightly lower in energy than the 3d orbital. Again, nature doesn't have to make sense. If our experiments show that the 4s orbital is lower in energy than 3d orbital, then that's the way we have to go. All right, so after the 4s, now we are at the end of this arrow. We got to start the next arrow. 3d is next. After 3d, now we can continue on to the 4p, 4p followed by 5s. Once the 5s orbital is filled, this arrow is over. Got to start the next arrow, and we can start adding in to the 4d orbital, followed by 5p, 6s, and so on and so forth. As I mentioned before, we don't have to go past this point because every element on the periodic table fits within these orbitals. Alrighty, so the next principle we need to look at is called the Pauli exclusion principle. Named after Wolfgang Pauli, he discovered that no 2 electrons in an atom can have the same 4 quantum numbers. If 2 electrons had the same 4 quantum numbers, they would be occupying the exact same space with the exact same spin, and that's just not very stable. As such, 2 electrons occupying the same orbitals must have opposite spins. So if one is a positive half, the other one must be a negative half. It can't both be positive half. Alright, so the last guideline for filling electron orbitals is called Hund's rule. Named after Friedrich Hund, he discovered that electrons occupy each suborbital of the same energy level with spins in the same direction before spin pairing occurs. So going back to our analogy, if you have 2 empty bedrooms, why would you want to share a bed? Everyone should get their own bedroom. Only if all 3 bedrooms are filled up and you have no choice, now you should start doubling up. Just make sure you have opposite spins. Just remember that as you fill up each suborbital, the electrons must spin in the same direction. And so by convention, we typically write them in as a up spin. Only once you have filled out every suborbital and are forced to double up should you now have down spins. So this one is incorrect. To correct this one, it should have been in this direction instead. Alright, so let's go over an example together. Let's go over the electron orbital diagram for magnesium. Now you don't have to draw boxes for every single one of them. That's pretty time consuming. Instead, you might want to just draw lines like this. That's what typically students will do. So just make sure that the 1s is lower than 2s because we are still drawing it in increasing energy levels. So notice how 4s is lower in energy than 3d. All right. Just use this diagram to assist you in determining which orbitals should go next and in what order. All right. So magnesium has 12 electrons we need to worry about. So that means I need to fill in 12 electrons. So first I'm going to use Aufbau's principle, which says I must always build up from the lowest energy level to the highest. So I'll start drawing from the bottom over here with my first electron. Now remember, each suborbital can hold a maximum of 2 electrons, but the Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. So make sure that if you are going to double up, they must have opposite spins. So I'm going to give this guy over here an opposite spin. So according to Aufbau, I'm going to move on to the next energy level. After the 1s orbital, so I'm going to cross that off, I can move on to the next one, which is 2s. So again, I'll draw it in over here, and then using the Pauli exclusion principle, put the second one again, but with an opposite spin. Once 2s is done, our next one is 2p. So I'll fill that one in. But remember that Hund's rule states that you must occupy each suborbital of the same energy level with spins in the same direction before you can start pairing up. So I'm going to continue drawing over here, and now that I'm forced to double up, go in the opposite spin, opposite spin, opposite spin. Now so far I've drawn 2, 4, 6, 8, 10 electrons. Magnesium, however, has 12 electrons, so I need to do just 2 more. Having finished 2p, I can now move on to my next energy level, which is 3s, and I'll draw in my last 2 electrons. Alright, so that is how we draw our orbital electron diagrams, or how we fill them in, using the Pauli exclusion principle, Hund's rule, and the Aufbau principle. What I would like you to do now is try out the remaining 3 questions over here. So in the first one, I've drawn the diagram for you. What I want you to do is identify which element you think it is, and then I want you to draw the potassium atom and fluorine atom in their ground states and fill in their electron orbital diagrams. Alright, so press pause. When you're ready, press play and we'll go over it together. Alright, so for the first one, what we're going to do is essentially just count the number of electrons we have here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26 electrons. We can then check out the periodic table to see who has 26 electrons, and that of course is iron. And so we write in iron. Alright, so moving down here, let's take a look at potassium. Potassium has 19 electrons we need to draw in. So remember the Aufbau principle says we need to start from the bottom and make our way to the top. Then the Pauli exclusion principle says you can't have 2 electrons with the same 4 quantum numbers, so you must have opposite spins. After the 1s orbital is the 2s orbital, so we'll fill that in, and then again with an opposite spin. After the 2s is the 2p. But Hund's rule says that we must fill in every suborbital first before we start doubling up. After 2p is 3s. So again, Pauli exclusion to double up. After 3s is now 3p. So again, Hund's rule. Then Pauli exclusion to make sure we have opposite spins. Let's count how many I've drawn so far. 2, 4, 6, 8, 10, 12, 14, 16, 18. But potassium needs 19, so we'll put in just 1 more. And there we have it, the orbital or electron orbital diagram for potassium. Now if you recall, potassium is a group 1 element, so it should have 1 electron in its valence shell. And valence shell means outermost shell, and so in our outermost shell, look at that, 1 electron in the outermost shell, and it matches up for potassium. Alright, so let's move ahead to fluorine. Fluorine has 9 electrons we need to draw in, so let's do that. So again, the Aufbau principle says let's work our way to the top. So there's my electron at the very bottom, followed by the Pauli exclusion principle, which says I must double up with opposite spins. Then I'm going to move ahead again. And now Hund's rule says I must fill up every orbital first, or suborbital first, before I am forced to double up. And when I do double up, I'm going to use the Pauli exclusion principle so I can have opposite spins. Whoops, got a little too overzealous there. 2, 4, 6, 8, 10, but I'm only supposed to have 9 electrons, so I'm just going to erase the last one over here. And there's fluorine. So let's double check to make sure what we drew is correct. Fluorine is a group 17 element. It's a halogen. Halogens have 7 valence electrons. Going over here, we see the outermost valence electron for fluorine contains 2, 4, 6, and 7 electrons. Alright, so if you're ever asked to draw an electron orbital diagram, this is what we're asking you to do. Again, you don't have to draw in the squares. That does take up a lot of time. Just draw in lines, and that's also acceptable. Just make sure that you're drawing the orbitals in order of increasing energy. Now, because these orbital diagrams take up so much space and a lot of time, we can shorten them and condense them into something called an electron configuration, where we just write them out. There's no need to draw in every single electron. So for magnesium, I would just write out 1s, and there's 2 electrons here, so I'm going to write out the number 2, followed by a 2s with 2 electrons. That is then followed by a 2p, but this time it has 6 electrons in it. Alright, and that's followed by a 3s2. And this would be the electron configuration for magnesium. So instead of writing out this big giant orbital diagram, we may ask you to just write out the electron configuration for it, and there it is. Let's try iron. Press pause, and when you're ready, press play, and let's see what the answer looks like. Alrighty, so let's start. It's going to be a 1s2 because there's 2 electrons, followed by a 2s2. That's followed by 2p6. Then a 3s2, then it's a 3p6. Now after 3p6 we don't go to 3d. After the 3p is a 4s. Then we can go to a 3d afterwards. So I'm going to write out the 4s2 followed by a 3d, and this is a 2, 3, 4, 5, 6, 3d6. Alright, and that would be the electron configuration for iron. Try out potassium and fluorine, please. And there you go. 1s2, 2s2, 2p6, 3s2, 3p6, and a 4s1. And fluorine is a 1s2, 2s2, 2p6. Please press pause and then try out arsenic and strontium. When you're done, press play. So arsenic has 33 electrons we need to consider. So let's begin. We start off with the 1s, so 1s2, scratch that out, followed by 2s, 2s2, because s orbitals can hold a maximum of 2. After that is a 2p, 2p, and then the p orbitals can hold a maximum of 6. After 2p, we can scratch that out. We have a 3s. S orbitals can hold a 2. So then I can scratch that out. That's followed by 3p. Again, 3p6. I can then scratch that out. After 3p is a 4s. 4s2. Scratch that out. At this point, I'm going to double check how many I've drawn so far. 2, 4, 10, 12, 18, 20. I need to draw 33, so I'm going to keep going. After 4s, I can go to 3d. If you recall, d orbitals have 5 suborbital shapes. Each can hold 2, so it can hold a maximum of 10. So I'm going to write down 3d10. Cross that out. I've now written out 30 electrons. I need to draw out 33. So that means my p orbitals are not going to be filled out completely. I just need a 4p3. All right, so altogether I've got 33 electrons, and this would be the electron configuration for arsenic. With strontium, we have 38 electrons we need to factor in. So here we go. Start off with a 1s, 1s2, scratch that out, followed by 2s2, scratch that out. Then it's a 2p6, scratch that one out. Then that's a 3s2, scratch that out. Then a 3p6, scratch that. 4s2. And then after that, I can start with 3ds. 3d10. Scratch that out. Followed by a 4p6. Scratch that out, and I've now got 36. I'm supposed to have 38, so I'm going to write down 5s2, 5s2, scratch that out, and now I've got 38 electrons accounted for. And that is strontium's electron configuration. As you can see, drawing out electron configuration is significantly easier, or at least less time consuming, than writing out orbital diagrams because you got to draw in all these boxes, but still pretty annoying to write out, especially if the atom has a lot of electrons inside of it. So there must be a shortcut, and there is. That would be called the electron configuration shortcut, or the shorthand method, if you will. Now this method takes advantage of the layout of the periodic table and how it's already separated to S, P, D, and F orbital blocks. If you recall, S orbitals only have 2 electrons that they can hold, so 1, 2. P orbitals can hold up 6 electrons, so 1, 2, 3, 4, 5, and 6. D orbitals can hold 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And F orbitals can hold 14. You can count that yourself if you don't trust me. Now take a look at germanium. Germanium has 32 electrons that we have to factor in. But with the shortcut method, instead of writing out all the electrons that came before it, we can instead replace those with the noble gas that came before germanium. So that in this case would be argon. So starting with argon, we can then move on to the 4th shell. 4s1, 4s2, and after 4s2 is a 3d. And then we have a 3d1, 3d2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to write down 3d10. Cross out 3d10. Next is 4p. Now I don't need all the p orbitals, just the first two, 4p1 and 4p2. And there is my electron configuration for germanium. So we just write down argon, 4s2, 3d10, 4p2, and that is the shortcut method instead of writing out all these other electrons before that. Instead, we can start from the noble gas that was prior to that element. Now you notice over here it says n-1. That's because the d block is always one energy level below the s orbitals. So you see 4s, and then it goes 3d, 4s, then after that it's 3d. Well, we can do the same as well over here. 5s goes to 4d. So the energy level for s orbitals is always one ahead of the energy level for d orbitals. So there's the n-1. So 4s, 3ds. 5s, 4ds. 6s, 5d. The d's are always one less than s. And if we look back over here, s orbitals are always 2 energy levels ahead of the f orbitals. So over here, 7 would become a 5. And that's why it's a n-2 block. Alright, so after 6s, followed by 4f. Alright, so let's try out lead and see what lead looks like over here. Lead is number 82, so the noble gas before lead would have been xenon, so that's why we put square brackets xenon. After xenon, we can now start fresh on the 6s, 6s1, 6s2. After the 6s is the 4fs. Alright, so 6s is followed by a 4f. 4f1 all the way to 14 because it can hold a maximum of 14 electrons here, so that's the end of that one. So 4f14. After 4f14 are the 5ds. So 5d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5d10. After the 5ds are the 6p's. 6p1 and 6p2 is where we end off. And we have a 6p2 over here. Alright, so what I want you to do is press pause and try out the shortcut method for the electron configuration of barium and iodine. When you're ready, press play. Alright, so barium is number 56. 56, and the noble gas before barium would have been xenon. So I'm just going to write down square bracket Xe for xenon, followed by 6s1 and 6s2, and that's it. That is the electron configuration shortcut method for xenon. Otherwise, if you had done the long method, I don't think it'd even fit in the space over here. Alright, and with iodine, we have a 53. Alright, and the noble gas before iodine would have been krypton, I believe. Alright, so square bracket with a KR. We'll start from there, and that goes 5s1, 5s2, followed by a 4d1 through 10, so 4d10, and then 5p1, 2, 3, 4, 5, 5p5. And that'd be the shortcut method, or the short form method, for electron configuration of iodine. Alright, so the last topic we need to discuss is that of electron configuration discrepancies. You see, not every atom follows the Aufbau principle, building up in energy from lowest to highest in this particular pattern. This applies to about 20 elements altogether. But you know what? 98 elements out of 118, that's not bad. So when it comes to chemistry, you kind of have to accept that there's always going to be exceptions to the rules, and that the rules we make, although they're not perfect, they do a pretty good job. But in the end, they are just approximations of how we see the universe. But the universe doesn't owe us a nice, neat, easy explanation, unfortunately. But keep in mind, just because a rule that we created isn't perfect doesn't mean that it's useless. Take traffic rules, for instance. You're supposed to cross the street on a green light, but that doesn't guarantee your safety. However, following the traffic rules is better than not following the traffic rules in most instances. Same thing. Following the Aufbau principle isn't perfect, but it does a pretty good job of predicting the electron configurations for most elements on the periodic table. So let's take a look at one such exception to the rule. If you use the Aufbau principle to predict the electron configuration for chromium, you would predict argon, 4s2, 3d4. Unfortunately, experimental data shows us that chromium's electron configuration in its ground state should be 4s1 and 3d5. To account for this, it will suggest that electrons will sometimes promote themselves to a slightly higher energy level in order to partially fill a completely empty orbital. This is especially true for d orbitals. So if you recall, s orbitals and d orbitals are very similar in energy, with the d orbital only slightly higher in energy than the s orbital. This makes it easier for an electron in the 4s orbital to be promoted into the 3d orbital. Now, why would they do this? If you recall from grade 9, 10, and 11, the noble gases are the most stable elements of the periodic table, and they all have one thing in common, a full outer valence shell. So we say that a full valence shell must provide stability. This is known as the octet rule. Unfortunately, a few lessons from now, you will find that the octet rule also has exceptions as well. In any case, this data over here seems to suggest that not only are full valence shells going to provide stability, but half-filled shells also provide stability. So if you ever encounter a scenario where your d orbitals are off by just one electron to achieve that half-filled shell, promote from the 4s, and that way each of these is half-filled, and that provides stability. You would do the same in this scenario as well. Notice how this one is just one electron away from a full shell. Promote from here, from the 4s to the 3d, and that will give you a full 3d orbital and a half-filled 4s, so stable and also stable. Alright? Now, just be aware that what I've just taught you is not completely true. Just as we simplified things in grade 9, 10, 11 and told you that the valence shell could only hold 2 electrons, 8, 8, 8 forever, this method of filling in electrons is also a simplification. The Aufbau principle is not perfect. It is not the true way of describing how electrons fill their orbitals. But this is an introductory course, and we don't want to bog you down in the details that many students would find confusing, myself included. So, for the purpose of this course, just follow the Aufbau rule and make sure you know this one exception to the rule, where you must promote from the s orbital to the d orbital if it will provide you with either a full shell or a half-filled shell. Now, this discrepancy we just learned helps us to explain why some elements are multivalent. It doesn't work for all ions, but it does work for some ions. Take, for instance, iron. Iron can typically form two ions, iron 2+ and iron 3+. Because the s and the d orbitals are very similar in energy, we can remove the outermost electrons to form an iron 2+ ion where it lost the 2 electrons. But once those are gone, you'll notice that the 3d orbital is very close to having a half-filled orbital. Since that provides greater stability, we can get rid of this 3rd electron over here, and now you've lost 3 electrons in total with an iron 3+ charge. And in fact, the iron 3+ ion is more stable than the iron 2+ ion because of this. On the other hand, zinc is generally monovalent and only has a zinc 2+ charge. Once it loses these 2 electrons, it becomes zinc 2+. Now it has a d orbital that's completely filled, and that provides stability. So there's no reason why it would want to lose any more electrons beyond that. Thus, zinc is monovalent with a charge of 2+. Now again, this method of explaining ion formation is not perfect, but it does a pretty good job of setting you up for future courses where you'll learn about other variables to factor in.